In this video, we're going to talk about polynomial functions and behavior. So the functions and behavior. But before we get to that, we need to talk about what is a polynomial function. So this is the definition for a polynomial function. There's some number times x to some power plus another number times x to some other, smaller power, and then so forth, all the way to get to some constant. This a sub n, the highest term, can't be equal to 0, because if it is, then you should have started here. Also, if n is 2, this is a quadratic function. Okay, so this may look a little familiar. When we had n equal to 2, we just had a2 x squared plus, some other constant times x plus some other, constant. Okay, so when n equals 2, this is a quadratic function, so it's familiar. But when n is higher than 2, we just call it the polynomial function. It's a more general term. Okay, so here I have an example. Really, this should say f of x equals, for this to be a function. Okay, so here's an example of a function, a polynomial function, and we can see that it's of degree n equals 5, right? Because the highest power here is 5. All right, another thing that we need to talk about is a power function. So a power function is basically x to the n, right? So everything else is 0 in the polynomial function. So power function just doesn't have the rest. So for example, x to the 4th, right? And this would be of degree 4. Okay, so now let's talk about n behavior for power functions, and then we'll build that up to understanding n degree or n behavior for polynomial functions. Okay, so these graphs, we kind of know what these graphs look like. Y equals x squared looks like this. Okay, y equals negative x squared looks like this. And y equals x cubed looks like this. And y equals negative x cubed is flipped. Okay, should go through the origin there. Alright, so, we kind of know what these graphs look like. We talked about them before. Also, just through experience, you probably know what these graphs look like. Alright, so let's talk about the n behavior of each of these. So what does it mean, n behavior, right? So when we talk about n behavior, what we do is we look for when y approaches infinity, and then we look to see what x is doing. Alright, so y is approaching very large numbers, very high up there. Y is approaching infinity. What is x doing? Okay, x, as y approaches infinity, x, and that over here, is approaching negative infinity. Alright, so let's write that. So y approaches infinity as x approaches negative infinity. Y also approaches infinity as x approaches positive infinity. And that's what you see happening over here. So x is getting really, really big, and then so is y. So that's what n behavior is. All right, let's do the n behavior for the next one. So say x is going to negative infinity. What's y doing? Y is also going to negative infinity. So let me draw a line here, separate this. So y approaches negative infinity as x approaches negative infinity. And then over here, as x is going to negative infinity, where's y going? Y is also going to negative infinity. So y is going to negative infinity as x goes to positive infinity. Okay, let's do this one. Here, as x is going to negative infinity, what's y doing? Y is going to negative infinity as well. So y goes to negative infinity as x goes to infinity. Oh, negative infinity is what I meant to say. Negative infinity. Okay? Then what happens when x goes to positive infinity? Y also goes to positive infinity. Y is going up. Okay, So y goes to infinity as x goes to infinity. All right, last one. So as y goes to infinity, or let me erase that. First, let's think about this. So here's x going to negative infinity. What's y doing? Y is going to positive infinity. So y is going to positive infinity as x is going to negative infinity. And then on the other side, as x is going to positive infinity, what's y doing? Y is going to negative infinity. So y goes to negative infinity as x goes to infinity. All right, so that's the end behavior of these four functions. But I have good news, which is these two end behaviors are going to be the same end behavior whenever the power function has an even n. Okay, so here the power function's degree is 2. So this end behavior, though, this end behavior is the same for all power functions with even n. Okay? And then over here n equals 3. Okay, and so this end behavior is the same for all power functions with odd n. All right, so other power functions like x, x to the 4th, for example. It's going to look maybe slightly different, do something else, but it still will have the same end behavior. And then if x to the negative 4th, again, so it might be doing something else, but it'll have the same end behavior. If you had x or y equals x to the some odd power, so like say x to the 5th, it might be doing something else in the middle, but it's going to be doing the same end behavior. Y equals negative x to the 5th, something different, same end behavior. Okay? So just as long as n is odd, you will have, the end behavior looking like this, and then if n is even, the end behavior will look like that. Okay, so now that was the end behavior for power functions, but I said I was going to talk about the end behavior of polynomial functions. So, now let's show that the end behavior of a power function is the same as the end behavior of a polynomial. Okay, so let's show that this is a polynomial. Let's show that f of x is approximately x squared, which is power function, when x is very large. The absolute value of x is very large. So that means it goes to negative infinity or positive infinity. Okay, so let's go ahead and do this. So f of x equals x squared minus 5x plus 3. So what I'm going to do is I'm going to pull out an x squared, right? So I'll be left with 1 here. And if I pulled out an x squared, this term, it only has 1x to give. So it's going to give that 1x, and then I'm going to need to divide it by x. Right? You can double check this. If I were to take this term and multiply it in, I'd be left with negative 5x. Okay? Then if I go over here, I'm going to have to divide this by x squared. Right? If I were to multiply it back in, they would cancel and I'd be left with 3. Okay? Okay, so I just use the distributive property to pull out x squared. Okay, so say x is getting really big. Say x is getting really big. Okay, so x is getting so big that this term and this term become 5 divided by 100,000. That's a really small number, right? These terms are 3 divided by, a million, right? These terms get very close to 0 as x gets really big. Okay, so f of x then approximately will equal x squared, right? X squared times 1 basically, because the other terms go to 0, right? And so that's the same thing as just saying it approximately equals x squared. All right, so at the end behavior the end behavior of x squared is the same as the end behavior of this polynomial. And in the next video, I'll talk about the leading term test, which will solidify this idea. So just, to restate this conclusion, so the conclusion is the end behavior of a polynomial is determined by the leading term. And that's the conclusion of the previous example.